I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined as always by my co-host Taylor Sparks, and this time by Eric Eierman, the CEO of CalNano. Eric, would you like to introduce yourself?
Yeah, thanks. Thanks, guys. Thanks for having me on. It's a great opportunity. Happy to be here to talk about SPS and some other stuff that we're doing. I'm the CEO of, like I said, CalNano, or California Nanotechnologies. We're a company that does SPS, basically everything you could think of: tool services, equipment, tooling, and even simulation software. Myself, I have a chemical engineering background, and started out CalNano as an intern, and I've worked my way up now to CEO.
So that's pretty awesome. From intern to CEO, you don't hear about that every day. It's kind of interesting to do this episode because a lot of companies reach out to us and say, hey, your audience might be interested in this technology or whatever. But this episode's kind of the other way around. I've been using your company as a service in my role as an academic for quite a bit longer than even the podcast has been around. So we are delighted that we could make this episode work. Now, if folks haven't listened to our previous episode on so-called Spark Plasma Sintering, that's episode number 35, maybe pause this, go listen to that, and then come back to this, because today's episode is, it's building on what we talked about last time. So Eric was he's a listener to the podcast, which we think is fantastic. And he reached out to us and said, hey, there's been some cool advances in moving this technology out of the research space where they're testing and proof of concepting it into actual industry, and let us know about some really cool technologies that have been happening since then. So Eric, in your discussions with me, we talked about things like ultra fast high temperature sintering. We talked about degas mode, fast cooling mode, different shapes, different waveforms, the size and shape of these things getting absolutely wild, maybe even bringing costs down. So we would love to get into all of these topics and more with you on today's episode.
Yeah, that's going to be great. There's a lot of new innovations that are happening now in the space, and it's going to be great to discuss all of them here.
So what's something that you are most excited about in the field of electric field assisted sintering?
I would say the size and the scale up. That's probably the most exciting for me, just because it has been traditionally used and seen as an academic tool. And now to see companies using it to make parts that are, up to 2 feet in diameter, large plates, and now even exploring, making tall billets, and then, on top of that, complex shapes, that sort of stuff is really, really exciting. And I think it's really going to push the technology forward into a lot of different applications.
Yeah, so one of the times I learned about this was on a grant from Idaho National Labs, where we were helping fabricate some of their materials. And these were high entropy alloys. And they said that they wanted to test them at large sizes. And I assumed that meant maybe they're going to go like an inch or two. And we had you guys making for us, what were they, 80 millimeter tall and 80 millimeter diameter pucks? That's big. That's like a coffee mug big. Like, these were way bigger than anything I'd ever made before. And that sort of shocked me. So now for you to tell me that actually there are tools out there that can go up to half a meter, right, is absolutely mind-boggling. Yeah,
it's really exciting. Yeah, I remember us making those parts. And that was pretty cool with the high entropy alloys. Be able to make those parts that size, and even our system can go up to about 150 millimeters in diameter or so. So then to look at these other people like Idaho National Lab now, who has the machines that are making 600 millimeters of size is kind of, it's almost mind-boggling, but it's really great
And
to
it's
see.
a big deal too, right? Because it's one thing to just be able to make this material with, getting close to its theoretical density and having these great properties in terms of its microstructure. But if you can only make these small little pucks that are only good for characterization, maybe micro hardness testing or something like that, it doesn't really do any good from an industry perspective. And so actually being able to achieve things of greater size starts to bring it into the realm of possibility and into potential applications where those properties can be harnessed.
So one question I have with this, I think back to when I was an intern, way like 20 years ago. I was working at Ceramatech, and I remember I don't even remember what application it was, but they wanted to make this ceramic rod that was 1 inch in diameter, and I think it was 9 inches long. And we, obviously the right thing to do is to isostatically press that, but for some reason, they were like, hey, just try and uniaxially press that. And I tried, and like we went to, I don't know, what a typical like 100 MPa or something, and we go to unload this thing, and it's like pure powder inside. Like it is not compressed at all. And now obviously I take my ceramic engineering courses and I learn about the die wall friction and how this is going to then reduce the pressure, the compaction pressure of the stuff in the middle of your die dramatically. How are we not getting those same sorts of problems as you scale up to really big components? Or is it the case that there's really big heterogeneity in those components?
Yeah, so you're definitely still seeing those issues when you're getting too tall. So when you get that aspect ratio where that height is really getting up there, you're still seeing those same things. I mean, the few of the things that we've done is basically be able to control your thermal gradient. So you're getting the you're getting the center to be able to densify or whichever kind of part of the longer piece that you're trying to densify, get that to one part to densify sooner, get that hotter, and then everything else can kind of sinter around that. So that's kind of one of the ways that we've been able to mitigate some of that stuff. But talking for that kind of aspect ratio, 1 inch to 9 inch, that's still definitely a challenge.
Yeah, to be fair, it was a really bad idea at the time. I think it still is a bad idea. But that was an illuminating moment for me to realize that the geometries are not all possible, right? Because of things like die wall friction. So tell us about CalNano. How did you guys get involved in this space, right? So have you always been a sintering company, or did you do something else and then move to this?
So yeah, it's a funny story. I mean, about over a decade ago, we just kind of stumbled into sintering, into SPS technology. So we're producing a nanocrystalline material with one of our other technologies, cryogenic milling. Basically a process, you're taking powder and you're making nanomaterial. Could be particle size or it could be actual like nanograined, nanocrystalline. And we needed a way to consolidate it, so without compromising the microstructure. And so we found SPS. It was an effective tool to do that. And so we bought an R&D system. It wasn't really until 2016, 2017 that we got really all in on SPS. And that's when we bought our big system that we have now that, we've done work with you on. And like I mentioned, that goes up to about 150 millimeters diameter. And yeah, from there, we've just continued to grow the business, grow out the network of customers, a lot of R&D work. And really now our goal is to transition a lot of this R&D work that we're doing into manufacturing, into commercializing the technology in all the different industries that we're working in.
That is super cool. So you've, in our discussions, you've told us that they're actually not only getting towards larger, but you've also mentioned that they're starting to move towards other shapes, even maybe net shaping. How on earth do you do that? Because anybody, I'm guessing, who's done SPS has been a cylindrical die. You wrap it with the foil, maybe you put the foil on the top and bottom. You've got a sort of penny-shaped sample. How do you do anything other than that?
Yeah, well, that's definitely the standard. And that's what you primarily work with, especially in anything that's research or you're making test samples. But when you go to more complex shapes, first thing you could do is tooling. So making, basically getting your tooling CNC'd or specialty made where you can get, dome shapes, you can get lenses, you can get tubes, that sort of thing. As you get more complex, there's new techniques, happening now where they're combining, a 3D printing or binder jet printing process, where you can, make either an inverse mold, and then you put that in, you load powder around it. There's methods where you're basically putting in powder, and then you're putting some sort of sacrificial layer, or like a separation layer in between, and then powder goes in, and then one side's the just kind of your excess stuff, and then the other side is your actual part. And so there's a lot of work being done in that area. Still definitely on the developmental side, but it's promising.
And these aren't trivial shapes either. I think you sent an article out of the University of Toulouse in France by Charles Meunier, and they demonstrate that they're able to use SPS, not only to just fabricate things like spheres or sort of polygons and shapes with lots of different edges and contours, but they even go so far as to manufacture a complete turbine blade using a single SPS. And so, that's a non-trivial geometry to press in an SPS. And so it's pretty impressive what they're able to actually achieve now in terms of shape complexity, with even, somewhat rudimentary and simple methods as just using sacrificial molds.
Yeah. And actually one of those blades was actually done here at CalNano. So he came, Charles, he came to CalNano, and, we did it in our larger SPS system. And and I remember him taking it out. So you're basically just, what's going in is you're just sintering a normal kind of, it looks like it's just a normal cylindrical part, and then you take it out. And I remember him like banging on the part, basically to break off the sacrificial part of it, to then what comes out is the final net shape turbine blade. So that was definitely an interesting thing to see, but it worked really well.
And how do you separate the sacrificial from the part you're actually interested in densifying, right? You can put some sort of sacrificial form in there, but is there some sort of interlayer between the part of interest and the sacrificed or mold?
It depends. I think they've come up with a few different methods. I think they're kind of proprietary at this point. I know that, obviously there's different methods that we use now for kind of interface layers, like, foil or boron nitride or those type of kind of lubricant, separation layers. But that's kind of what it is. It has to be a thin piece that is going to allow you to, take apart those things. And like I said, even with that, it was still had to be broken apart, essentially.
So presumably you could use a lot of the same techniques that they have used for hot pressing of complex shapes. The only thing that comes to mind of concern is here you have to have electrical conductivity. Are you just getting that through the die, or is there an attempt to try and influence net shaping with respect to conductivity of the powder itself?
It's definitely a combination of both. The first thing you want to try, is just using a kind of things that are done in hot pressing, and regardless of conductivity, you just get the heating through the mold, and you still have the advantages of really high heating rates and electric field that's being generated, all that sort of stuff. But yeah, as the kind of things continue developing, that's definitely something that's going to be kind of worked on and looked at, is how to keep that benefit of being able to conduct, when you're using conductive powder, to get that current going through the entire thing.
So one of the innovations that I've become familiar with is the ability to degas mid-process or shortly after the process. What's really the motivation behind that?
The idea there is for powder purity. So if you have any type of material that is, I'm sure you guys have seen in the SPS process, when you're starting to ramp up, you're seeing that outgassing, that vacuum spike during the heating process. And the idea with the degas is to be able to do that, to heat up your material, then be able to remove that top punch, which then allows for the kind of maximum amount of outgassing of purifying your powder, and then go back to your full sintering cycle.
Is it hard to get that? When I've done this, you take a lot of care when you're lining it up initially. It's got to be just so lined up just right. Now you're saying you're going to actually back that punch out and then you're going to reinsert it. Do you run into cracked dies or misalignment issues by doing that?
It's definitely possible. It's definitely something that you have to really take care to make sure you're all properly aligned. But if done well and you set yourself up, your tooling up right, then it can work really well.
So is this a new technique that your companies are? Well, first up, maybe I should back up and say, are you guys selling machines or are you selling a service with machines made by other people? Where do you guys fit in this dynamic?
Sure. So we represent a company. Their name is Suga, and they're a Japanese SPS manufacturer. Have some of the best people there. Kind of some of the originals that developed like the big tunnel type systems over in Japan. Have decades, of SPS experience, and so we are their North American distributor. And so we essentially sell machines here in North America for them. So that's our business in terms of on the machine side. And then obviously our other business is toll services, like, kind of we've mentioned there that, we take material from customers and we will sinter it for them using SPS.
Okay. So obviously one advantage of degas is you get rid of impurities. Are there any other advantages to that mode? And is that novel? How long has that not been around for a while, or is this a new thing?
This is a new one. Yeah, this is a new development from Suga on their lab scale systems. And I think the difference is being able to have it where you can take out kind of in situ during the sintering process and then insert it back in.
So to do that, the top punch must be fastened in some way to the upper piston. How are you doing that?
So it's mounted. Yeah, so it's mounted up to the spacer above it. Typically with something like bolts, graphite bolts, that sort of thing.
So another innovation I've seen out of your flyers is this idea of fast cooling mode. That definitely captures my attention because everyone talks about SPS or, it's so amazing you can sinter materials in 5 minutes or in 10 minutes. But there's this huge but. It still takes 2 hours for the thing to cool down. And even then you're taking it out at such a high temperature, sometimes it's oxidizing, right? So, and that's with water cooling running down to the pistons and the ramrods. So how on earth are you guys doing fast cooling mode?
So it's basically where you're taking usually inert gas and you're basically blowing it directly onto the mold or onto the punches or any combination of that, and blowing that cold gas is what is allowing you to kind of enhance the cool down rate. So it's nothing as fast as say like a quench or anything to that extent, but it does have can have an appreciable benefit in terms of the cool down rate.
Some ballpark numbers for us, for in the past when I've gone to say 1200 C, it might be 1 or 2 hours with a coffee mug sized die. With this cooling, what sort of things could we expect to see?
Somewhere half that. Yeah,
that's way cool.
And it really depends on the exact geometry of the die, and obviously there's factors in terms of how fast you can actually cool it. Is your sample going to crack? There's all those things to take into account.
And there's huge benefits to cooling faster, right? I mean, that residual heat is going to contribute to grain growth, which can, offset a lot of the properties that are desirable in SPS, right? If you can achieve nano-grained materials early on, but then during the cool down cycle, those grow to be a little bit bigger, that's not ideal. And so being able to cool faster makes a lot of sense there. And gives it certainly an advantage over maybe hot pressing, which doesn't cool down nearly as fast.
Yeah, exactly. And then same thing, for hot pressing, comparing it there, obviously the heat up rates, play a factor. So definitely has advantage when it comes to, keeping those that nanocrystalline structure.
I suppose another way to cool things down faster is just to reduce the amount of mass in your die. Of course, as you move to thinner and thinner walls, then it gets weaker, and these things are already breaking pretty regularly. But I guess you could use stronger materials. I know there's die materials, silicon carbide, and others. I'd be curious to see what impact that has on the ability to cool things even faster, is using just less thermal mass, right, around the component.
Oh yeah. There's definitely been developments in terms of different toolings, and obviously the tooling that is going to have the kind of want to expel heat the most is going to be the one that's going to cool down the fastest.
Are there surface treatments you can do to these? So essentially, what you're doing with blowing gas is you're adding convection to what used to be a conduction problem, right? Are there surface treatments? So this is I'm a material scientist and not a mechanical engineer, or maybe I would know the answer to this. But are there also surface treatments you could do to sort of maximize the way that blowing this gas on it pulls heat off of these things?
Yeah. I mean, there's ways basically of kind of aiming the gas, and how you have to determine how fast you want to kind of pressurize it, and like I said, exactly where it's aimed, the angle, that sort of thing. So that's all. There's a basic way that you're just basically getting gas on there, and that's going to speed it up. And then as we kind of continue to work on the process, we'll figure out what's going to be the most effective.
So what role has modeling played in, determining how you're going to optimize these things, or improving your understanding of certain processing conditions, whether that's just in fast cooling alone, or maybe in just the design or operation of these systems in general?
So we've only kind of, I'd say, dabbled in modeling. Really haven't had the personnel in place to do a lot of work in, let's say, ComSol to make our own thermal modeling. But we have now teamed up with a company called Gemini over in France, and they've made a really simple to use kind of thermal model. You can see thermal gradients. You can see tooling stresses. But that's definitely a big, going to be a big component now on how you can determine what's happening in your system. An example I like to give is we had a boron carbide project we were working on, and we're getting to a temperature, and we kept melting out, and we just had no idea why. And so then we ran it through the simulation, and we saw that actually at the center of what we were reading, obviously you guys know, we're reading at the die wall, just inside, and what we're getting at the center was actually just above melting. And when we brought that temperature down just 25 degrees, all of a sudden, no melting, everything was great. But the simulation showed exactly that. And so kind of that's how we're looking to use the simulation software to give us a better indication of how to do those sort of things.
That's huge, because so much of it is just trial and error. When I've used these tools in the past, it's like, we had a ton of flash, let's try and go a little bit lower. It's a huge pain, especially if it took a lot of effort to synthesize the powders to start with. You can't just like blow through 20 grams with trial runs. So being able to simulate that is pretty awesome.
Yeah, and that's the whole idea. And with this tool, it's really cool because it's so simple to use. I know that I've talked to other people, kind of in your position in the past, that have using ComSol. It's real hard to set up, and you have to have someone that knows the software and be able to set up design of experiments and all that. With this one, I mean, you can set it up, and you could set up your experiment in a few minutes, and you let it go, and then boom, pops out your kind of nice diagram of thermal gradients and all that, the tooling pressures and all that stuff.
So another thing listed in your brochure had to do with selectable waveforms. I'm a little more skeptical about this, and I'm curious what you think are some of the big advantages that come from tunable waveforms. So in our last episode, we talked about whether or not electromigration or anything of that nature is really playing a prominent role. So when it comes to waveform, what sort of advantages do you see with a tunable electrical waveform?
I really see it as a great kind of research tool and exploring that area more. Because obviously people have explored the pulse versus DC, and that's had some effect on materials, certain materials, but not as not too much, only very specific materials. But then the other wave, like a full waveform, that really hasn't been explored as much. So I think it's going to be very interesting to certain researchers to see what kind of effect that has on their material properties, electrical properties, that sort of thing.
So in other words, we don't know yet, but now we can at least look, right? Now we have a way to look.
Yes. Yeah, exactly.
Fair enough.
That's the idea.
Would you be open to discussing some of the challenging SPS cases you've had and how you've overcome them? Even if you can't get into any of the material details, maybe just, trying to use this technology and trying to harness all of its benefits in challenging sintering situations.
Yeah, sure. I can definitely get into that. So, one of the projects that we worked on, it was with a metallic, it was a metal powder, and we were, requested by our customer to be able to embed a wire inside of it. And that wire had to be, it was also metallic, but it had to be completely electrically isolated from the part itself. So we had to sinter powder around it, but then keep it so it was completely isolated from the wire. And so that's a significant challenge, because any coating you're going to put on there, that I've kind of been able to find is typically with any other sintering process, you're going to go way too hot, you're going to melt, it's going to be, it's going to be a mess. And so with SPS, because we were able to sinter at such low temperatures in comparison to other processes, we were able to put on that coating and effectively, isolate that wire from the kind of external, metal body. And so that was a pretty cool achievement that we had with SPS, that I can say that I don't think that many other processes could have been able to pull off.
And did you have to make special dies to orient that wire? Because, in my limited experience with SPS, I do know that trying to include other objects within the sintered body, they can get affected by the currents and displaced during the operation.
Yes. Yeah, we had to make a special die, special tooling design to be able to, because that wire had to stick out, obviously, and so you're sticking out on opposite sides. You had to make sure that was kind of aligned properly, and so we had to make special tooling to make sure that stayed in alignment while sintering was occurring. And like you said, yeah, the making sure there was no conductive path from wire as you're sintering to get any hot spotting, any sort of thing like that. So yeah, that was all part of the extensive kind of process we did to develop it.
So one of the repeated reasons why I think SPS could be a displacive, innovative technology just is cost. Instead of these really slow ramp up times, now you can get to temperature fast, maybe even get out of temperature quickly. Do you actually have some numbers for us on how much sort of cost or energy savings we're talking about for a company?
Yeah, there've been some studies done, and obviously just from firsthand experience, we're talking with some, with certain programs up to an 80%, energy savings when it comes to the SPS versus say a hot press, and then obviously in terms of time, where you can get a part or multiple parts if you're doing any type of stacking or multi-sample tooling, you can get parts out in, like you said, a few hours versus a hot press. It's going to be 24 hours, plus you're doing anything large. So that's a big savings as well. But on the energy side, the thing I'd kind of point out is that, using a hot press, you have to heat up a whole furnace. So you're heating up this massive chamber. Everything has to be heated up to the same thing. Versus SPS, your heat is all focused on exactly where you want it. And you could even really focus it when it comes to like changing your tooling for like a thermal gradient or um, focusing on a bond line. So really focusing your heat in one specific area. So yeah, that just kind of picturing that in your head of like you're only heating the very small area versus an entire chamber. You can kind of visualize how that would
big
be
advantage
a big
there.
energy savings. Yeah.
Are there any new sensors or probes that you guys are looking at to sort of gather more information from real-time measurements? Way back in the day, the ones I saw had a pyrometer looking basically at the temperature from the outside. You could drill a little hole and try and look towards the middle. You could put a thermocouple in there. And then a few years later, I saw the German SPS company was actually putting a pyrometer looking straight up. And so you could sort of get an idea of the gradient through the sample. Has there been more innovation in this space?
Those are still the primary ways that you're measuring your temperature during the process. I think the real kind of innovation is when you can use the simulation software in kind of congruence with those, and so you can again maybe you do a first trial, you actually put a thermocouple or something that goes all the way to the center of the part. You run your kind of sacrificial part, and that gives you kind of is approximately what the center temperature is. And then you have also one that's on the outside measuring temperature. And then from there, you can use that data with the simulation software to then kind of predict how things are going to happen, for different things moving forward, with that particular material. But in terms of new sensors or probes, right now that really hasn't been a big focus that I've seen in the community.
You kind of mentioned that there is some trial and error to it. So when you're given a new sample, some client comes to you wanting to make a new material or have that SPS'd, how much of it is trial and error versus applying your own previous theory and sort of knowledge about SPS and just experience with what sort of failures can occur?
Very dependent on exactly what material they're coming to us with. If it's something that's the same or similar to what we've done, then yeah, we will be able to use kind of previous work when it comes to parameters, temperature, pressure, hold time, that sort of thing, and be able to quickly typically get to a point where we're getting to full density or whatever properties they're looking for. If it's something more kind of nuanced, it's a really novel material, then that will be more trial and error. That will be more kind of first, using our SPS in what we call a manual mode, and basically just watching displacement and watching the curves as we're increasing temperature. And that will give us an indication of how's displacement going. When does it level off? Do we start to see any sort of expansion, any melting that occurs? And then from there, our kind of expert operators can gauge, in a few runs, how where kind of the optimal level is, after analysis of the part.
So here's another question for you, Eric. I'm curious what sort of fields or industries you feel have been sort of dramatically transformed by the advent of SPS.
So, big one is high entropy alloys, refractory alloys. So, these materials, kind of background on those. Obviously, they're metallic materials that are really resistant to heat and to wear. So they're great for extreme environments. Think hypersonics, think space, nuclear applications. But because of the high melting points of them, they're really hard to process. But SPS is proven now to be a great tool, kind of as you mentioned earlier, that we did the work with INL, to be able to sinter those. And so it's something that is in the transformation process, I would say, because those kind of materials are pretty new. They're still all being developed. But I think that's a big one that is going to use SPS for a long time to make these kind of next generation advanced materials.
Going forward, what do you think the future holds for this technology? Is it basically done being innovated, or is there a lot more to be done?
Oh, I think there's a ton more to be done. I think there's a lot of innovation. It comes to the complex shapes, comes to expanding the technology into manufacturing. So that's going to be a whole new challenge. As we're getting now, there's only a very small amount of companies that are using it in any type of real like high volume manufacturing applications right now. And so a lot of innovation is going to have to be done there, utilizing other industries, other kind of things like that are already being done, like hot press and high volume, but using that to be able to make these advanced materials with SPS, but also in a high volume manufacturing sort of area.
So big thanks to our sponsor for today's episode, CalNano. We've been talking with Eric Eierman, so you've heard how, CalNano is a leader in this area of SPS manufacturing. They've been in the business of advanced material science and R&D in manufacturing for quite a while. They are the #1 provider for R&D manufacturing toll services for SPS in North America. Like I said, I've used them in the past before and had really good experiences with them on some of my federal grants that I've been working on. Their programs can range from a few samples to full-scale R&D and production products made with SPS. And notably, I think it's cool, he mentioned that they work with the manufacturer, Suga, and this company, Suga, has released the instrument, the SPS 2000, that has some of these interesting and unique features that we talked about in today's episode, things like degas mode, rapid cooling mode, or the selectable waveform. So I think those are cool things to keep in mind if you're considering purchasing a new unit as well. And then finally, CalNano is not just in the business of selling machines and doing this as a service, but they also sell a lot of the tooling and the consumables that go into using one of these devices. So things like dies and the components therein. They have a machine shop that allows them to fabricate specialized parts to order. So if you need some of those components, maybe look them up. Our podcast is also sponsored by Materials Today. Visit materialstoday.com and you can stay up to date with everything that's happening in the material science field, and always you can read some of the really cool articles that they have published. And it's obviously more than just a journal. They are also really about building community. You can check out the other books, conferences, and related programs that they have for offer.
And as always, thank you for listening to this episode of the Materialism Podcast. If you have questions or feedback, please send us emails at materialism.podcast@gmail.com. Make sure you subscribe to the show on iTunes, Spotify, Google Podcasts, or wherever you listen. And if you like the show and want to help us reach more people, consider leaving a review. It helps us improve and it exposes new people to the show. Finally, check out our Instagram page at materialism.podcast and connect with us to let us know what new material you'd like to hear about next. Before we go, we'd like to give a shout out to Alphabot and Kolobyte for making the music for the podcast. They both make a ton of really cool synthwave music, so go check them out on Spotify and YouTube. Catch you next time.
Till next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world, and are bound only by their imaginations in manipulating those materials.